Hello, we are Group 4B in the Intro to Physics lab. For our Algodoo project, we're going to explore the topic of collisions. We observed many aspects of collisions, but most specifically momentum, velocity or change in velocity, energy, and whether or not these quantities are conserved in each collision. Um, for our first scene, our model contains two identical objects. You can see the two blocks on the screen. One slides down the ramp and hits the other, and they both move to the right of the screen. In the scene, the both objects are completely identical. They have the same mass and the same size. And this we use this to demonstrate conservation of momentum and energy. At the moment, right before the collision, the first object has a positive non-zero velocity, and the second object is completely stationary. The first object's velocity comes from its change in energy from potential to kinetic energy. You can see at the top of the ramp, it is above the ground, and so it has some level of potential energy, and that energy is all conserved to kinetic energy as it slides down the ramp. We know it's all conserved because we turned off any other losses through thermal energy, like friction on the ramp and on the block, and air resistance. We turned those off so that is so that it's a more like perfect transfer of energy from potential to kinetic. Um, we intended to have like a perfect elastic collision. So as the block slides down the ramp, the two would collide and stick together. And when they would collide, the velocity of the system would be half that of the velocity of the two block system would be half that of the initial velocity for the first block. But because of because we're not really sure why, but Algodoo doesn't allow us to, or it's not showing us this perfect collision where they would stick together. And we've turned off all possible frictions in the system, and we've also turned off the like elasticity of the blocks, so like how bouncy they are. It has a more Clayton, what was the specific word for that?
The restitution. We turn the restitution to 0.
Right, which Algodoo describes as the bounciness. And we turn that down to 0 and they still won't stick. So this is just more of a demonstration of how like life isn't always perfect. You're not going to get a perfectly inelastic collision. And I guess at this point we can move on to the second scene.
I'd also add that we changed the material of both the blocks to wood, and we changed the material of the ramp to ice.
Okay, for our second scene, we illustrated a car rolling down a ramp and hitting a more massive car. Due to gravity and the conservation of energy, the car picks up speed as it rolls down the hill. And this is because its original potential energy at the top of the hill turns into kinetic energy, which means an increase in velocity. The car has a positive momentum right before it hits the second car, so it has a positive velocity. And then the steel car, the more massive car, begins to move with a positive velocity after the collision. Because our system is defined as both cars, in order to conserve momentum, they will each be moving with a smaller velocity than the initial speed of the first car right before the collision. This is because we added mass to the system, so we had to decrease the velocity in order to conserve momentum. And after the collision, since the steel car has a larger mass than the first car, it will move with a slower velocity because of the M1v1 conservation of momentum laws. And we can see the forces acting on the car as it rolls down the hill as included in our force diagrams. And then that is all I have for scene 2.
Also, in this scene, we added the momentum vectors on the steel car so that they're small, but if you look, you can see once the car collides with the steel car, then the momentum vectors are pointing in the positive x direction.
Okay, and then our third scene models a collision when a motor is involved. So we have one car with a larger mass that's stationary and a car with a smaller mass moving with a positive velocity to the right, and it's getting this positive velocity from a motor. And then when we have the collision, when the moving car hits the stationary car and collides, the stationary car begins to move in the positive right direction also, but it doesn't move as fast as the initial velocity of the moving of the smaller mass car before the collision because of the conservation of momentum and because it has a larger mass. Momentum is conserved, so since the initial velocity of the system is not zero, the final velocity of the system is also not zero due to the equation m1v1 equals m2v2. And then we ignore the other external forces such as friction and air resistance, so we can assume that our equation that we use accurately represents this model, and the cars will move at the same velocity eternally because it's in the x direction.
And we added the plot to the top so that you can see how the velocities move before and after the collision, and just gives more of a visual. On to 4.
Yeah.
Okay, this is our last scene that we made. We created a pendulum that starts at an initial height above the ground, which gives it an initial potential energy, so that when it swings, when it is at the lowest point, it'll have kinetic energy, and since at the lowest point, it has the most kinetic energy in its swing. That's where we put the collision between the car and the pendulum. When it collides, the pendulum, or I guess more the ball that swings with the pendulum, will transfer a lot of its kinetic energy into the car, but not all of it. So this is an elastic collision because kinetic energy is not going to be conserved, but momentum will be conserved. So if you watch first, once the collision happens, the car will roll up the ramp and roll back down. But once it rolls back, it'll collide again with the pendulum, which then, if you watch the plot up top, you can see how the energy is changing because of the velocity. So if we restart, we also added a laser attached to the ramp at the top right here, so that when we go up the ramp this time, we can cut the rope, and then you can watch how the car rolls to the left with almost the same velocity as it was rolling to the right before it went up the ramp. So that's a really good representation of two things, momentum and conservation of energy. We're mostly focusing on the conservation of momentum and collisions, but the energy is also a very cool part to this scene. Once the collision happens, the car gets momentum and it rolls up the ramp to a certain point where it stops instantaneously and then rolls back down. And because we turned off friction on the ground, or no, we didn't turn off friction on the ground, we turned off air resistance. So because we turned off air resistance, the energy will be conserved. Once it rolls back down, it'll have the same velocity as before it rolled up the ramp. So that was our final scene, and this was our project on modeling collisions.